The question is, please read this. A rectangular loop of width A and length B is located near a long wire carrying a current I. The distance between the wire and the closest side of the loop is C. The wire is parallel to the long side of the loop. Find the magnetic flux through the loop due to the current in the wire. Okay. Suppose we move the loop to loop that is shown in the figure very far from the wire, then what will happen to the magnetic flux? So let me first draw the diagram that is given in the question. They have given one wire. Okay, this length of the wire is I, and sorry, current to the wire is I, and the wire is actually very long. There is also one more rectangular coil that is kept close to it. The rectangular coil has two sides. One is this having A as the length, and the other side is this one having B as the length. And the closest length, the closest side of that rectangle is at a distance of C from the wire. Now using this, we have to find out the flux that is passing through this coil. Now finding flux is very easy. I think all of you know the formula that flux is equals to B into A general formula. Vector formula would be vector B dot vector A. That's the formula. But if you want to find out flux, there is another formula which is integration of B dot dA. We generally use this formula whenever the magnetic field is a variable, right? Same thing is happening here. Throughout the area of the coil, the magnetic field is not a constant. My magnetic field is actually varying. First of all, which direction is the magnetic field acting? Can we find out? Because of a current carrying wire, finding magnetic field is always done by using right hand thumb rule. You can try holding the wire by using the right hand, and you find that the fingers are curling in this way. That means my finger is trying to go into the board. That means magnetic field would be into the board in the entire region of the coil. But the magnetic field produced by a current carrying wire depends on the distance. If you know the formula, then magnetic field is given as mu naught I by 2 pi r, where r represents the distance from the wire. That means with different distance from the wire, I am having different magnetic field. So I cannot directly use this formula to find the flux. I will have to use the second way. Now if you think of it, my magnetic field is changing with the distance. So if I am at same distance, if I am at a constant distance from the wire, let us say x, then everywhere at that distance, everywhere at that same distance x, can expect to have the same magnetic field. Now if I go a small distance ahead, a very small distance, if I go ahead from here, right, this much small thickness I'm going ahead, and that distance I'm going ahead is dx, then what can you say about the magnetic field in this shaded part? Remember, the distance that I'm moving extra is very small. It's a small dx. So because of that small change in distance, the change in the magnetic field would be also very small, insignificant. That's why we'll consider for this very small strip, the magnetic field would be constant. And how much is the magnetic field here? Means the magnetic field B would be equals to mu naught I by, same formula I'm using, 2 pi divided by x. That is a magnetic field in that region. So using this magnetic field, can I find the flux for the small region? For the small region, the flux can be called as d phi, and that is nothing but the magnetic field into the area. Okay, actually it should be B into dA into cos of theta, because it's a dot product, right? So cos theta, what is the angle theta? First of all, which direction is the magnetic field? We use right hand thumb rule, and we saw that it is going in. And for any area, the area vector should be also perpendicular. So area vector is perpendicularly inwards, magnetic field is also perpendicularly inwards, the angle between them is 0. So my equation will become now the B value mu naught I by 2 pi x, area value should come, and then it should be cos of 0, because both area vector and the magnetic field is in the same direction, that is into the board. What about the area of this strip? Because I'm finding magnetic flux for this strip right now. What is the area of the strip? If you just see this, the strip is also in the shape of a rectangle whose length is b and whose thickness is dx. So I can say it is b into dx, that is the area. Now, once I got the magnetic flux for this small region, now I can find magnetic flux for many such strips and add all that magnetic flux. I'll be able to find out the total magnetic flux. So if I want total, I should do integration of d phi. That would be my phi, the total flux. And that would be here. Integration, what is the variable here? Cos 0 is anyway 1, that's gone. Mu naught IB, everything is constant. 2 pi is constant. So let me take it out. Mu naught IB divided by 2 pi. Integration of 1 by x dx. What will be the limit of my x? My x will be changing starting from a value of c until c plus a. So I can have this as c to c plus a. So I'll get total flux is equals to mu naught IB divided by 2 pi. Integration of 1 by x is natural log of x. When you put the limit, that is c to c plus a, you finally get the flux value as mu naught IB divided by 2 pi natural log of C plus A by C. So this is the flux that is passing through this region. So a very important thing for the students to understand here is, generally I always prefer to use this formula for my flux wherever my magnetic field remains constant throughout the area. But if the magnetic field is not constant, you cannot use the first formula to find it. You definitely have to find the flux for a small strip. That strip could be in the shape of a rectangle, it could be in the shape of a ring. All those things depend on how the magnetic field is varying. Now you can see that magnetic field is varying with the distance. So that means at same distance, I'll be having same magnetic field. And if I go slightly further with a small dx distance further, I'll be having still the same value. The change will be very minimum. But that's why the shape has automatically now converted to a that rectangular shape. But it depends on the question, it depends on the magnetic field. Don't always take the strip, it depends. Let us say if you had the same wire like this, okay, and you're interested in finding the magnetic flux generated by this at some distance, because on a loop, same question. So again I have to take the same strip. But what if your magnetic field was directly proportional to r, or depending on, let us say, the circumference? I'll show you some questions later. Some exact questions will come later in the video. At that time I'll show you. Anyway, so while choosing the strip, you have to be careful with the distance. That's the important thing, right? How the magnetic field is changing. Because the magnetic field is changing with the distance, that's why I took at same distance. Okay, fine. Now, anyway, I got this as a flux. The next part is what will happen to the flux if this coil goes to infinity, very far away, they are saying. If it goes to very far away, then can I just rearrange this as phi is equals to mu naught IB divided by 2 pi natural log of 1 plus A by C. And if the coil goes very far away, then C will tend to be infinity, right? C tends to be infinity. Very, very big it has become. If that is the case, then if I put that here, then obviously my answer will convert to what? Flux is equals to 0, because instead I'll be getting C is infinity means A by infinity will be 0. So natural log of 1, and natural log of 1 is actually 0. So if the coil goes to very far away distance, flux will be 0. As the coil comes towards the wire, the flux keeps on increasing. I hope all of you have understood this. We'll stop the video here. Thank you very much.